Hey guys, welcome to another video of quantum field theory. In today's video, we'll be continuing off from the last video and finishing up the calculation for the Hawking effect. So let's continue. So in the last video, we derived this relation over here for the right part of the quantum field. We said that this part represents the term of the field that enters the collapsing sphere, and this part is the one that leaves it. That seems a bit dubious to me, but let's just go on from there and see what happens. So to find this term over here, what this form is going to be, we need to first write out Q in terms of U. Recall that Q is actually a function of U. We want to find out what Q is in terms of U. And to do that, a good way to do that is to find the derivative of Q with respect to U. Because from there, we can just do separation of variables and then integrate, and then we can find out Q in terms of U. So we can just use the chain rule. This is just dq over d tau over du, plus dq over dr over du. And recall again that r is going to be a function of proper time. It's the radius of the sphere as it collapses. So this is going to be equal to, well, dq or d big Q over d tau. That's just 1. So you have d tau over du. And then minus, because dq over dr is minus 1. So we have this over here. We can now just combine these two, because we can distribute through the division part. And now we have this over here. Now, how do we actually find out what this is going to be? Well, we can do that by matching the metrics. So we talked about how the exterior metric and the interior metric describe the space-time outside and inside the black hole or the collapsing sphere. Now, these metrics need to match at the actual boundary of the sphere, right? So to have continuous geometry, the metrics have to be the same at that boundary. So by doing that, we can actually find the form of this. That will make sense later. Let's actually go through the math first. So first of all, we need to write out du in terms of d tau. Du is just du over d tau plus, dt, because it's not a function of tau explicitly. So dt, then plus du over dr asterisk. So this means that dq over du is d tau minus dr over dt minus dr asterisk. And now what we can do is we can do some things. So all the r, right? It's a dynamical variable, right? So we can write dr out as dr over d tau. And that's going to be dr equals r dot d tau, where r dot is just defined as dr over d tau. All right, we can also write this as d big R over d tau. Big R and small r mean the exact same thing, so it doesn't really matter. So this means that dq over du equals d tau minus r dot d tau. Well, what's dr asterisk? Well, dr asterisk, recall, is just dr over c of r. So this is going to be minus dr over c. And then dr, again, is just going to be r dot d tau. And now over c. Is we can factor out the tau part over here, giving us 1 minus r dot d tau c d tau. Okay, so now these taus cancel out, and we're left with this relation over here. Now, you guys might say, yeah, you don't have any proper time terms anymore, but the problem is we still have one right over here. So how do we find out what that's going to be? Well, to do that, we can define some dummy variable, f, where f equals t. So dt over d tau is just going to be df over dt, which we can just call f dot. okay? So to find f dot, what we want to do is match the metrics. So the metric for outside the sphere was c of r du dv. We can also write that out as dt squared minus dr asterisk squared. We not derive this, but like we kind of like talked about this in the video on the Hawking effect. So if you don't know where this comes from, just watch that video. And analogously, the metric for inside the sphere is going to be, and what we want to find out, what we want to do is find out what f dot is going to be. So to do that, we need to match the metrics. So we set the metrics for outside the sphere and inside the sphere to be equal to each other on the boundary of the sphere. And this makes sense intuitively because we want our geometry to not have any jump discontinuities. So like along the world line of the collapsing sphere, like we want like the outside metric and the inside metric, right, to be the same right along that boundary of the sphere. Okay, so that kind of makes sense from a physical kind of viewpoint. So we want to do that. So first of all, we need to introduce proper time into this part of the equation. So recall that dr asterisk is just dr over c, and then dr is just dr over d tau times d tau, or r dot d tau. This means that this left-hand side becomes term there, and this will be r dot squared and then d tau squared. Okay, now what we can do is we can factor out a d tau on both sides. That would give us, so all we've done is you just factored out the d tau on both sides, the d tau squared to be specific. And now what we can do is we can divide both sides by d tau squared. And remember that this right over here, we said that was f dot squared, since f dot was just dt over d tau. So this means that c times f dot squared minus this squared. We can use some rearranging here to find that f dot squared minus r dot over c squared equals a times 1 minus r dot squared over c. Then by doing some more stuff, just basically algebra at this point, we are going to find that f dot over, or f dot is going to equal the square root of this right over here. Now remember that dq over du, we said it was this right over here, highlighted. It's this right over here. And we can just plug in the formula that we found for f. It's going to be pretty hefty, but it's going to end up being this. What we can do to make this a bit less ugly to look at is we can multiply both sides by c over c, which is just 1. And what we can do is we can factor out this part over here. So just taking a look at this yellow part right over here. If we were to like zoom in here, what we have is a times 1 minus r dot squared over c plus r dot over c squared. So that's just going to be the same thing as r dot squared over c squared. We can look at it like r dot squared divided by c, right? Now what we can do is we can just put this under one denominator, and then since we have the c in front, right, we have c times c to the minus 1/2, which is just c to the 1/2. So basically, we can just move this c to the front, and that'll be c times this entire thing, and then we don't have to worry about this one anymore. It's just algebra, really, but with a lot of variables. And then now we can distribute the c on the inside. That'll be ca times 1 minus r dot squared. And then there's this was a plus, by the way, sorry. And then plus the c will cancel out with this c once it goes in there. So you'd have a r dot squared. So this term pretty much just becomes c times 1 minus r dot. And we're going to have a minus r dot because this would cancel out with this one over here. And this, by the way, this is not in the, what's it called, square root. It's not in the square root, just note that. And this is our formula for dq over du. We are finished. Now what we do is we want to look at how C of r behaves near the horizon. We can see that C approaches 0 at the horizon. That's kind of how we define the horizon. There's a singularity there. So taking C going to 0, we can approximate this as this much simpler expression right over here. How do we go from this to this? I'm not exactly sure. It probably is some like mix of the hospital rule or the L'Hopital rule or something like that. Whatever it is, you can simplify it like that as C approaches 0. Doing some rearranging stuff, we can get this right over here. And to find Q as a function of U, we want to expand R of T near the horizon. Since we're taking C near the horizon, we should take R as well to be consistent. So we can just do a Taylor expansion for R of T. It's going to be this. This is the formula for a Taylor expansion. If we want to switch the terms in here, we'd have to add a minus sign there. So we'd have that. Therefore, this equals that. We should also expand C of R near the horizon, like we kind of already did that right over here. But that was just for like C as a constant itself. But if you want to write C as a function of R near the horizon, we'd have to do another Taylor expansion. Of course, C when R equals RH is just 0, right? So giving us this right over here, just a Taylor series. And then by just putting C of R back into this expression right over here actually, and then plugging in R dot for this over here, we arrive at this expression right over here. Pretty cool, huh? So now what we want to do, also, by the way, in case anything is weird, H and small h and big H, they represent the same thing, by the way. I accidentally wrote a big H for one of them. And also, big R is the same thing as small r, which is the same thing as big R of T. You get the idea here. So I don't know why some textbooks write them as different letters, one capital, one lowercase. So I'm just gonna write it like that if in case anyone's trying to follow along in some textbook. So going forward, what we want to do now is divide both sides by r minus blah blah blah, and then we know that we can just flip this, so we have dq times minus r minus rh, and by doing that we can cancel some things out. We can cancel that with this one right over here, giving us a negative sign. Remember that q is tau minus r plus r naught, right? And that's what we have here. Big R is the same as small r. So small r is just going to be q minus tau minus r naught. Sorry, no, that's minus small r, right? So this means that we can just plug in this in there. That'll give us 1/2 partial c over partial r du equals dq. That's what I love about Texas. And then rh, and then you had a minus r, so that's going to be plus q minus tau minus r naught, then minus 1. This tau here is going to be a tau h, since you're looking at how the C of R and R of T behave near the horizon. So we're going to have tau of h instead of just tau there. So what we can do now, note that this is an integral over dq. Well, we'd have to actually integrate first. Take the integral on both sides. Sorry if this step is kind of confusing. It is pretty weird, honestly. So it's this over here, tau h minus r naught minus 1. Doing the integral, we're going to have 1/2 partial c over partial r times u. And then this is going to be minus natural log of rh plus q minus tau h minus r naught minus 1. Okay. So what do we do now, you may ask? Well, we're going to have a constant of integration plus c here, and we can kind of, I'm not sure if this is rigorous, but we kind of ignore this -1 for some reason and kind of try to absorb it in that constant of integration. And then we can do the same thing for r naught. So now what we can do, we can define some new constant called kappa. That's partial c over partial r. What's that going to be for a Schwarzschild black hole? Well, taking the derivative of some things, we're going to have r minus 2m, or plus 2m actually, over r squared. Actually, kappa is defined as 1/2 partial c over partial r. So that means we're going to have 1/2 times, what was it, 2m over r squared for kappa for when c is Schwarzschild like. And then we call the r equals 2m at the event horizon. So this is just 1/2 times 2m over 4m. And then this cancels out with this. Actually, no, there's going to have an m squared here. So this cancels out with one of these. And this is going to give us 2 over 8m. And that's just 1 over 4m. So this means that the surface gravity is going to be 1 over 4m. So kappa corresponds to the surface gravity of the black hole. So just a small side note. So now we have kappa u plus d here, because this is also a constant of integration. We're going to switch c and d's together because textbooks will tend to have c on this side. So we're going to have ku plus c equals the natural log of all of these things. We can absorb this and this into the d thing. So natural log of q plus d. We can take an exponent of both sides. That'll give us e to the ku plus, or times e to the c. We can just call that new constant c. This is going to equal, also before we do that, we should, technically speaking, multiply both sides by -1. And then we can just add both sides by positive d. And that'll give us that q equals c e to the ku plus d. And this should actually be a minus ku because of the minus sign that was over here. So now we have found our formula for q. And now we can look back at our field, phi of v. We said that this was the incoming field and this was the outgoing field. This is actually a v, by the way, even though it might look like a u. So what do we do now? We found what q was as a function of u. Now what we can do is we can recall that this over here was just v, right? The fancy way of writing v for when we are at the center of the black hole. So we can assume that at late times, v actually behaves like u. Okay, we can assume that v behaves like, actually like, not like u, like q. Okay, there is some physical justification for this, but I don't really understand it fully because my textbook skips a lot of steps. So let's just kind of assume, I guess, that v behaves like q at late times. I mean, the actual reason, right, is that dv over ds, you'd find that's going to be equal to a times 1 minus r dot over 2 r dot. Like doing the same steps like before we found what dq over du was. But if you instead find what dv over ds was, and again looked at c approaches 0, you get this over here. But then my textbook does like some magic and says, okay, now therefore this over here. I'm not really sure what the in-between is supposed to be, but I don't want to spend more time figuring it out. So let's just assume that v behaves like q at late times, okay? So if that is true, this means that phi of v is going to be e to the minus ikv minus e to the minus ikq, okay? So v behaves like q. But we found that q was this over here, right? So this means that we have e to the minus ikv minus e to the minus ik times c e to the minus ku plus d. Okay, these are just constants, right? We can set them to whatever we'd like. So yeah, we're actually pretty much done here, almost though. So again, this is the ingoing wave, this is the outgoing wave. Let's actually graph these guys and see what they mean. But before we do that, this is a kappa. So this is a K, this is a kappa. They look the same, right? So I'm just going to call this something else. Let's call this J, I guess. So e to the minus I, or e to the minus ju, where J is just 1/2 partial C over partial R. So let's graph this guy, see what it looks like. So here I've graphed these two functions in Desmos. So the red function represents the quantum field that is like not disturbed by the sphere yet. So the incoming quantum field. The outgoing quantum field is one in the blue. They were exponentials, right? The way we actually wrote them out. But we can kind of describe exponentials like e to the ik something as sinusoids because of Euler's formula, right? So that's why we can write them as sine of whatever. So we see that for the blue term, we had that exponential in there. And because of that, there's a redshift. So you guys can actually see the redshift as we get farther and farther away, right? It redshifts more and more. The wavelengths start to increase each oscillation, and then finally this kind of like dies out. However, for the incoming wave, it's like the same thing. It's just like a basic sine function. So you can see how the redshift happens, and we want to compare the red field, the red guy, to the blue guy basically through the Bogoliubov transformation. So let's do that. So for the Bogoliubov transformation, we can take this to be the outfield, this to be the infield. You just plug them in here, and this over here is just the inner product that we talked about in a video on the transformation. And if we were to actually do that, we would get a super complicated expression that contains the gamma function. The steps to solving it, it's pretty clunky. So we'll leave that to the mathematicians to stress over. So, but basically, if you were to do all the math, you would end up getting an expression for beta, and then we can take the squared value of beta, take an integral, and we get this for the exposition value for the number operator. And this kind of looks like a Bose-Einstein distribution, and this would imply a temperature of J over 8 pi m if we were to match this to what we have here, similar to what we did for the Unruh effect. So yeah, that's pretty much it for today's video. If you guys want to see the calculation for the Bogoliubov transformation, I can link that in the comments if you want. So yeah, thanks for watching this video. This is the end of the Quantum Field Theory 2 series. The next video will be a summary, and from there we'll move on to interactions. See you guys then. Bye.